802.10 LAN security. This standard provides a secure pathway for data across a shared path. An implementation of this standard is used, sorry, an implementation of this standard is using the public internet as a backbone for a private interconnection between locations. The term for this form of connecting is known as virtual private networking, VPN. Because VPNs cost less than direct private connections, VPN is likely to become popular in the near future. The 802.11 wireless LAN. Wireless networking usually requires a higher upfront investment than cable-based networking. Still, the cost can be justified in an office if an office is rearranged with any regularity or must be moved from one location to satisfy business requirements. Recently, 802.11 was updated to include the 802.11b standard, which specifies higher wireless standards, 11 megabits instead of 1 megabits per second for the original 802.11 standard. This demonstrates that the 802 standards have not been static for 20 years. Instead, they've been a dynamic set of rules that continue to be updated as technology moves forward. The 802.11.12 demand priority access method, first developed by Hewlett-Packard. This standard combines the concepts of Ethernet and ADM. The communication scheme used is called demand priority, thus the name of the standard. It uses intelligent hubs to allocate more bandwidth to frames that have been assigned a higher priority by the sending computer. Hub scans its ports and then allocates bandwidth according to each frame's priority. This is extremely valuable for real-time audio and video transmissions. The 802.12 standard is also known as 100VG voice grade, 100VG ANI-LAN, 100 base VG, and ANI-LAN. The 100 is short for 100 megabits per second, or 10 times faster than the original Ethernet speeds. Other manufacturers didn't buy into the ideas of 100 base VG, perhaps in part because of the higher overhead of demand priority due to port scanning. Instead, they updated the original Ethernet to fast Ethernet, which also supports 100 megabits per second. While maintaining the 802.3 standards. The following table summarizes the main features including speed, access method, topology, and media, or various technologies such as 802 standards and FDDI. Main features of various network technologies: technology, speed, access methods, topologies, media. IEEE 802.3 speeds 10, 100 or 1000 megabits per second. Carrier sense multiple access, collision detection, logical bus, coax or UTP. IEEE 802.5 4 or 16 megabits per second. Token passing, physical star logical ring STP, IEEE 802.11b, 1 or 11 megabits per second, carrier sense multiple access collision avoidance, cellular non-wireless, FDDI 200 megabits per second, token passing, physical star logical ring, fiber optic UTP implemented as CDDI. Data link layer devices. Three main devices manipulate data at the data link layer: bridges, switches, and network interface card. There are more complex they are more complex than their physical layer counterparts, and thus are more expensive and more difficult to implement, but they each bring unique advantages to the network. The bridge. A bridge is a network device operating at the data link layer that logically separates a single network into two segments, but it lets the two segments to appear to be on one network to higher layer protocols. The primary use for a bridge is to keep is meant to keep traffic solutions on one side of the bridge and not to let it pass to the other side. For example, if you have a group of workstations that constantly exchange data on the same network segment as a group of workstations that don't use the network much at all, the busy group would slow down the performance of the network for other users. If you put a bridge to separate the two groups, however, only traffic destined for a workstation on the other side of the bridge will pass to the other side. The switching hub. In the past few years, the switching hub has received a lot of attention as a replacement for the standard hub. The switching hub is more intelligent than the standard hub in that it can actually understand some of the traffic that passes through it. A switching hub, or switch for short, operates at the data link layer and is also known as layer 2 switch. Layer 2 switches build a table of the MAC addresses of all the connected stations. When two stations attached to the switch want to communicate, the sending station sends its data to the switch. This part of the process is similar to the way a standard hub functions. However, when the switch receives the data, rather than broadcasting it all out the ports as a hub would, the switch examines the data link layer header for the MAC address of the receiving station and forwards it to the correct port. This port opens a virtual pipe between ports that can use the full bandwidth of the topology. Switches have received a lot of attention because of this ability. If a server and several workstations were connected to the same 100 megabits per second Ethernet switch, each workstation would need a dedicated 100 megabits channel to the server, and there would never be any collisions. The OSI's middle layers. As you move up the OSI model, the protocols at each successive layer get more complex and have more responsibilities. At the middle are the network and transport layers, which perform the bulk of the work for a protocol stack. The network layer. The network layer of the OSI model defines protocols that ensure that the data arrive at the correct destination. This is probably the most commonly discussed layer of the OSI model. Network layer concepts. The most important network layer concepts are logical network addressing and routing. Logical network addressing. In the last section, you'll learn that every network device has an address, the MAC address, assigned at the factory, and that this address is protocol independent. But as you know, most networks communicate using protocols that must have their own addressing scheme. If the MAC address in the data link layer physical address, the protocol addressing scheme at the network layer defines the logical address. Each logical network address is protocol independent. For example, a TCP IP address is not the same as an IPX address. Additionally, the two protocols can coexist on the same computer without conflict. However, the two different stations using the same protocols cannot have the same logical network address on the same network. If that happens, neither station can be seen on the network. Routing. Routing is the process of moving data throughout a network, passing through several network segments using devices called routers. which select the path the data takes, placing routers on a network to connect several smaller routers turn a network into an entity known as an internet. Routers get information about which paths to take from files on the routers called routing tables. These tables contain information about which router network interface or port to place information on in order to send it to a particular network segment. Routers will not pass unknown or broadcast packets. A router will route a packet only if it has a specific destination. Information gets into routing tables in two ways, through static routing and through dynamic routing. In static routing, the network administrator manually updates a router's routing table. The administrator enters every network in the routing table and selects the port on which the router should place data when the router intercepts data destined for that network. Unfortunately, on networks with more than a few segments, manually updating routing tables is more time expensive and prohibitive. Dynamic routing, on the other hand, uses route discovery protocols or routing protocols for short to talk to other routers and to find out which networks they are attached to. Routers that use dynamic routing send out special packets to request updates of the other routers on the network as well as to send their own updates. Dynamic routing is the most popular routing technology. With dynamic routing, the two categories of the route discovery protocols are distance vector and link state. Older route discovery protocols such as Routing Information Protocol (RIP for TCP) and RIP for IPX use the distance vector method. The distance vector in distance vector routing, a router sends out its routing table when the router is brought online and the contents of its routing table every 30 seconds thereafter. When another router receives the contents of the router's routing table, it adds 1 to the hop count of each route in the list of routes and then rebroadcasts a list. A hop is one pass through a router. This process typically takes place every 30 seconds. The main downside to distance vector route discovery is the overhead required in broadcasting the entire routing table every 30 seconds. Link state route discovery is more efficient. Routers using link state route discovery routes send out their routing table via a multicast, not a broadcast packet. Every 5 minutes or so, if there is an update, only the update is sent. Network Link Service Protocol (NLSP) for IPX and Open Short Path OP OSPF for TCP/IP are two link state route discovery protocols. Several protocols can be routed, but a few protocols can't be routed. It is important to know which protocols are routable and which aren't, so that you can choose the appropriate protocol when it comes time to design an internetwork. Table 2.3 shows a few of the most common routable and non-routable protocols and the routing protocols they use, if any. Routable and non-routable protocols. Protocol route discovery and routable. IPX or IP, yes. IPX NLSP, yes. NetBEUI, no. TCP IP or IP, yes. TCP IP OSPF, yes. XNS RIP, yes. So I'm going to leave it here today for this video, If you enjoyed, please consider like, sharing, and subscribing. Thank you very much.